Hey guys, in this video we shall discuss properties of continuous time Fourier series. So we have like 9 properties. I'll just give you the statement here. I'm not proving it, but the detail of proving I have done it in discrete time. So I'm just giving you the statement here. Okay. We have like 9 properties, starting from linearity property to symmetry property. We shall see its statements one by one. Okay. So first property is linearity property, and its statement says that if x of t, a signal in time domain, as a pair, Fourier series pair, I mean x of t and x of k, these two, when I put an arrow mark, double-sided arrow mark here, it means that x of t, if you take it to frequency domain, I get x of k. X of k, if you take it to time domain, we get x of t. In the sense, it's a pair, a Fourier series pair. Okay. So if I take continuous time Fourier series with fundamental frequency omega naught, so these two are Fourier series pairs, right? So, and y of t, I have one more signal y of t, and if I take continuous time Fourier series with fundamental frequency omega naught, I end up with y of k, capital Y of k. So then so if I combine these two, a times x of t plus b times y of t, and if I take the continuous time Fourier series with fundamental frequency omega naught, so what I end up is a times x of k plus b times y of k. This is the result I should get if I combine the individual input. Okay, so this is the statement for linearity. Now time shift. So again, if I have a Fourier series pair f of x of t and x of k, if I take continuous time Fourier series with fundamental frequency omega naught, in time domain, if I shift the signal by t naught, right or left, this might be plus also, but usually we will take it as minus. Okay, so if I shift the signal and if I take its continuous time Fourier series with fundamental frequency omega naught, what is x of k gets multiplied with e power, you retain the sign, if you have minus you write minus here, j k, okay, so omega naught, and how many times you shifted, it is t naught, right? So omega naught t naught. So this is the statement. Fine. So now frequency shift. Again, if I have x of t and if I take continuous time Fourier series of this sequence with fundamental frequency omega naught, so I get x of k. Then if I shift in frequency domain, x of k minus k naught. If there is a shift in frequency domain with k naught, in time domain, so what happens is x of t gets multiplied with an exponential term. Okay, but here you have to reverse, change the sign. I have minus, you have to make it as plus. Okay, j, how many times you shifted? K naught times omega naught times t. Okay, now scaling, if x of t, I take continuous time Fourier series with fundamental frequency omega naught, I get x of k. Then if I scale the independent variable by factor of a, so and if I take its continuous time Fourier series with fundamental frequency omega naught, so I end up with the signal x of k. Okay, it does not change. Fine. So this is the statement for scaling property. Time differentiation. Again, if the signal in time domain x of t, I take continuous time Fourier series with fundamental frequency omega naught, I end up with x of k. Then if I differentiate the signal in time domain with respect to time and I take its continuous time Fourier series with fundamental frequency omega naught, so what happens in frequency domain is x of k gets multiplied with j, k and omega naught. Okay, this is the statement for time differentiation. Now convolution, if x of I have two signal x of t and y of t, if I take continuous time Fourier series for both the signal with fundamental frequency omega naught, I end up with x of k and y of k. Then in time domain, if I periodically convolve with x of t and y of t, whereas in frequency domain, it is nothing but multiplication with the scaling factor t, x of k into y of k. Okay, so this is nothing but circular convolution or periodic convolution. There is a circle here. Okay. Next is the modulation. Again, I have two signal in time domain, x of t and y of t. I take it to frequency domain using continuous time Fourier series with fundamental frequency omega naught. So I end up with x of k and y of k. Then in time domain, if I multiply these two, x of t into y of t, so I am multiplying the two signal x of t and y of t in time domain. So in frequency domain, what I end up with, convolution, x of k convolved with y of k, whereas here it is not circular convolution, it is regular convolution. Okay. Next, Parseval's theorem. If I have a signal in time domain x of t, and if I take it to frequency domain, I end up with x of k. This Parseval's theorem states that 1 by t integrating for one period, if you take magnitude square of the signal in time domain, okay, this ends up in frequency domain, summation k varying from minus infinity to infinity, magnitude square of x of k. Okay, integration in time domain is equal to summation in frequency domain, both has to be taken its magnitude square. Now the last property, if I have a signal in time domain x of t and I take it to frequency domain, which ends up with x of k with CTFS and its fundamental frequency is omega naught, then so first thing is, the first property in this scaling is x complex conjugate of k becomes x of minus k, its time reverse, its frequency reverse, if x of t is real. Fine. Next, second property is imaginary part of x of k, the Fourier series coefficient, becomes equal to 0 if x of t is real and even. Okay. And the third one is real part of the Fourier coefficient x of k is 0 if the signal in time domain is real and odd.